In this video, we'll learn about the distance formula. First of all, what is distance? Distance is simply the length or amount of space between two objects or points in space. Distance can never be negative. Examples of the uses of distance include finding the distance between two locations, finding the amount of distance covered by something or someone, or finding the amount of distance left to reach a certain point or location in space. Distance is a scalar quantity, encompassing only a magnitude that expresses it, such as 13 kilometers or 8 feet. It doesn't include direction, unlike vector quantities do. What formula should we use to find distances when dealing with coordinates? We need to use the distance formula, which states that distance is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared. So when we're dealing with ordered pairs, we usually denote their values with the components in the formula based off of the order we see them in. For example, if we're given 4, 3, and 5, 2, we'll denote their values with the components as 4 equal to x1, 3 equal to y1, 5 equal to x2, and 2 equal to y2. We're doing it in this order since we first see 4, 3, so we'll denote their values as x1 and y1. And secondly, we see 5, 2, so we'll set their values as x2 and y2. Let's apply this formula and do a few practice problems. Number 1, calculate the distance between point A and B given its coordinates. First, we'll assign the components in the formula their value based off the order we see them in, like we said before. So we'll denote -2 with x1, 4 with y1, -7 with x2, and -8 with y2. Now we simply plug them into the distance formula, which is distance equals the square root of x2 minus x1 squared plus y2 minus y1 squared. We'll plug it in as the square root of -7 minus -2 squared plus -8 minus 4 squared, in which -7 minus -2 becomes -7 plus 2. And this will translate to the square root of -5 squared plus -12 squared, which once again translates to the square root of 25 plus 144, which equals the square root of 169, and ultimately equals 13. Thus, the distance between points A and B is 13 units. Number 2, calculate the distance between point A and B given its coordinates. First, we'll assign the components in the formula their value based off the order we see them in. So we'll denote 4 with x1, -3 with y1, -6 with x2, and -8 with y2. Now we simply plug them into the distance formula, which states distance equals the square root of x2 minus x1 squared plus y2 minus y1 squared. So we'll plug it in as the square root of -6 minus 4 squared plus -8 minus -3 squared, in which -8 minus -3 turns into -8 plus 3. This translates to distance equals the square root of -10 squared plus -5 squared, which is equal to the square root of 125. In simplest radical form, this would be 5 square root 5. However, the approximate distance between A and B is 11.18 units when we round to the hundredths place. Now let's apply this formula and do a brain teaser this time. Number 3, calculate the perimeter of triangle ABC given points A, B, and C along with their coordinates. To calculate the perimeter, we simply add up the 3 edges lengths of the triangle, which would be in this case line AB plus line BC plus line AC. For the distance of line AB, since points A and B have the same elevation and y coordinate of their ordered pair, we can simply subtract their x coordinates to figure out the distance between the two. So we'll have line AB is equal to 6 minus -3, which is equal to 9. For the distance of line BC, since points B and C have the same x coordinate of their ordered pair, we can simply subtract the y coordinate to figure out the distance between the two. So we'll have line BC is equal to 7 minus -2. For the distance of line AC, we'll have to use the distance formula given the ordered pairs. For the coordinates of point A, we'll assign -3 as x1 and -2 as y1. And for the coordinates of point B, we'll assign 6 with x2 and 7 with y2. When we plug them into the distance formula, we'll have the square root of 6 minus -3 squared plus 7 minus -2 squared, in which 6 minus -3 becomes 6 plus 3, and 7 minus -2 becomes 7 plus 2. This translates to the square root of 9 squared plus 9 squared, which equals the square root of 81 plus 81, and ultimately equals the square root of 162. I won't take the square root of 162 and round it now, as when we plug it into the perimeter formula and evaluate it, we'll get a more accurate, closer result. Now that we have the lengths of all of the edges of this triangle, in which line AB equals 9, line BC equals 9 as well, and line AC equals the square root of 162, we can just plug them into the perimeter formula as 9 plus 9 plus the square root of 162 to get an approximate perimeter of 30.73 units when rounded to the hundredths place. Let's apply this formula and do another brain teaser. Number 3, find the length of the leg X or line AB in this right triangle given points A and C's coordinates. For this one, we're not getting a whole lot of information, so we'll just have to make do with what we're given. So, since the length of leg X or line AB's length isn't given to us, we must incorporate a trigonometric function to use in order to find line AB's length. So, line AC constitutes the hypotenuse in this right triangle. We can also say that leg X is adjacent to the 40-degree angle that is given to us, which is angle BAC. Given an adjacent side length and the hypotenuse that we can evaluate with points A and C with the distance formula, in fact, we should consider using the cosine function, as this function falls into the cap part of SOHCAHTOA, in which c equals cosine, A equals adjacent, and H equals hypotenuse. First, we have to find the length of the hypotenuse to set up a trigonometric equation. To do so, we need to use the distance formula. Given the coordinates of points A and C, we'll set 12 as x1, negative 8 as y1, 20 as x2, and negative 2 as y2. When we plug them into the equation, we'll do as square root of 20 minus 12 squared plus negative 2 minus negative 8 squared, in which the negative 2 minus negative 8 translates to negative 2 plus 8. This becomes the square root of 8 squared plus 6 squared, which becomes the square root of 64 plus 36. This equals the square root of 100, which ultimately equals the square root, which ultimately equals 10. Now that we have the hypotenuse's length of 10, and we have an angle measure, now we can easily set up the equation to find the length of leg x, or line AB. So we can set up as cosine of 40 degrees equals x over 10. To isolate x, we'll multiply by 10 on both sides to get cosine of 40 degrees times 10, which is equal to x. And therefore, when we evaluate that, it'll become 7.66 units long when we round to the hundredths place, which is the length of leg x, or line AB. So we've dealt with finding distances within a 2D plane using x and y coordinates. But what about finding distances within a 3D plane, in which we need to incorporate x, y, and z coordinates? The formula for finding distances within a 3D plane is practically the same as it would be in finding distances within a 2D plane. However, we just need to add an extra part to the equation to account for the value of the z coordinate. For finding the distances within a 3D plane, the formula for doing so is distance is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. As you can see, we're just adding the same structure we did for the x and y coordinates to account for the z coordinate, which would just be z2 minus z1 squared. So let's apply this new formula and do one practice problem. Number 5, calculate the distance between point A and point B, given its x, y, z coordinates. Remember, the process is the same for assigning the coordinates to their positions in the equations. So when we do, we'll assign 5 as x1, 3 as y1, and 1 as z1 for point A, and for point B, we'll assign 1 as x2, 7 as y2, and 11 as z2. When we plug these values into the equation, we'll plug it in as the square root of 1 minus 5 squared plus 7 minus 3 squared plus 11 minus 1 squared. This simplifies to the square root of negative 4 squared plus 4 squared plus 10 squared, which translates to the square root of 16 plus 16 plus 100. This simplifies to the square root of 132, which ultimately equals 11.49 units long when we round to the hundredths place. Thus, the distance of line AB in the XYZ plane is approximately 11.49 units long. For our last problem, we're dealing with a word problem, a real-life scenario. So it states a person decided to walk over to his friend's house using the path illustrated below by the dashed lines and dots, in which the dashed line represents direction and the dots represent a new direction taken. The start point, which is the person's house, is marked by the word start and its coordinates 10, 16. And the end point, which is the friend's house, is marked by the word end and its coordinates 2, 5. Calculate the displacement based off of the illustration along with the coordinates below. First of all, what is displacement? Displacement is simply the distance between the initial and final point, and it doesn't count for other distances within the system. Thus, the displacement in this scenario would be the distance between the start point, which is the person's house, and the end point, which is the friend's house. For the coordinates of the start and end points, we'll assign their components in the formula as 10 equal to x1, 16 equal to y1, 2 equal to x2, and 5 equal to y2. So when we plug these values in, we'll plug it in as the square root of 2 minus 10 squared plus 5 minus 16 squared. So this evaluates to the square root of negative 8 squared plus negative 11 squared, which simplifies to the square root of 64 plus 121. When we add 64 and 21, this equals the square root of 185, which when rounded to the hundredths place ultimately equals 13.60 units. Thus, the displacement of this scenario is approximately 13.60 units. Thanks so much for watching, everyone. I hope you guys enjoyed.